Magnetism. We'll start with defining magnetism and the magnetic fields. Talk about the origin and direction of magnetic fields. Where do they come from? Then the different forces that a magnetic field exerts on a moving charge and on wires and between two wires. Practical applications of the electromagnetic force. Then two worked out problems, force on a current carrying wire and the magnetic force on a moving electric charge. Magnetism and magnetic fields. Magnets were first discovered over 2,000 years ago by the Chinese and the Greeks and were used for various non-scientific purposes. The name was coined by the Greeks because certain magnetic rocks, which were later named magnetite, were found in the province of Magnesia, named after Magnesia. And unlike electrical effects, which we've studied in some great detail, which started by rubbing various substances together which would separate the electrical charges so you could see the attractive and repulsive forces, these magnets came out of the ground already and attracting and repelling certain materials. You didn't have to do anything to them. It took another 1,000 years before the Chinese, European, and Persian mariners, those are people who go to sea, separately used magnets for navigation. When you took a magnetic material, shaped it in the form of a little needle, and floated on a surface of water, it always pointed in the same direction, towards the North Pole. Always being able to tell which direction was north is a critical factor in ushering in the age of exploration. You had to know where you were going. And once you know north, then you know south, east, and west. However, it took another 600 years before William Gilbert explained what was going on. But first, let's talk about the nature of magnetism. Magnets have two ends, which we will call poles, called north and south. Like poles repel, so if I have two south poles near each other, they'll repel, or two north poles, they'll repel. Opposite poles attract. What is this analogous to? Well, certainly when we did charges, we found a plus and a minus attracted, and a plus repelled. So very similar here, except in magnetism we call them poles, and this is the magnetic force. When a magnet is cut in half, each piece still has a north and a south pole. No matter how many times the magnet is cut, the pieces still have a north and a south pole. You can never just get a pure north pole or a south pole. This works all the way down to the atomic level. So you can see we have a magnet here, we cut it in half. We now have a north pole here, a south pole here. Then on the other piece of the magnet, we have a north and a south pole. Cut it one more time. The exact same thing happens. We have a north and a south pole, north and a south. Nowhere do you cut this and then you would get one magnet with just the north pole and the other with the south. No, they both have a north and a south pole. So let's compare magnetic poles and electric charges. The behavior of magnetic poles, north and south, are very similar to the electric charges, which are positive and negative. North and south, positive and negative. Now, don't think that the north is like the positive and the south is like the negative. These are arbitrary conventions. Opposite poles attract and opposite charges attract. Like poles and like charges repel. However, there are two significant differences between these two types of force. One, certain materials are naturally magnetic. Where electrical properties, you have to have physical rubbing. They are not naturally electrically charged. And secondly, there are independent positive and negative charges. We did that the last couple chapters. We'd say we had a positive charge here, a negative charge over here. They'd attract each other, but they were two separate entities. However, magnetic materials always have a north and a south pole. You will never find a north pole by itself. Now you have to be careful saying the word never in physics and science. People are still actually looking for something called a magnetic monopole, where you would have just a north pole or a south pole. To this date, it has not been found. Electric field lines were used to show how electric charges would exert forces on other charges. We're going to use a similar concept here in magnetism. But what's nice about magnetic field lines is they are more easily seen, and I put that in quotes because you're really not seeing the lines. The above is a picture of iron filings. We have these little tiny pieces of iron, and we dropped them on top of a paper that was on top of a bar magnet. So let's see, can you see the magnet here? And we're saying this is the North Pole and this is the South Pole. All the magnetic filings line up in the direction of the field lines. Because iron is a magnetic material, it will act like little bar magnets in the presence of a magnetic field. They will align with the magnetic field of the large magnet. The field exits one end of the magnet, see, leaving here, and returns to the other end. And it comes back after going like this. We ran out of room on a little slide, but it goes something like this. And it comes back there. And also note, the field lines go through the center of the magnet, making a complete loop. Unlike electric field lines, if you remember there, I could have a plus charge here and a negative charge here, and the electric field line would just be that. It's a straight line. There's no complete loop. So we've shown how the blue line goes all the way around, completes outside the little picture. And then the red line here, that shows you a complete loop, leaving the magnet here, coming around, coming back in, and going back out. The key word here, or keywords, complete loops. Arbitrarily, which means we're going to use a convention here, somewhat like when Ben Franklin named the positive and negative charges, magnetic field lines are defined as leaving the North Pole of the magnet. You can see how the arrows are coming out of the North Pole and re-enter the South Pole. The lines specify the direction that the North Pole of another magnet in the field will point towards. So if I put a magnet here, which way is the North Pole going to orient itself? Well, the arrow is going this way, so the North Pole should point this way. This would be the North Pole. This would be the South Pole. If I put somebody over here, a magnet, the north would point in this direction, the same as the direction of the field. This would be the south. And again, these loops here that just look like they're going nowhere, they really go way out here and complete over here. We just ran out of room on the slide. Once again, all magnetic field lines form complete loops and go right through the magnet. Just like electric fields, different configurations of magnets will produce interesting magnetic fields. Here we have two north poles close to each other. We know they're going to repel. And look at these field lines. You can go back to the electric field unit and find out that that looks just like two positive charges nearby. And again, the arrow leaves the North Pole, just like in the positive charge, the arrows would go like that, the electric field lines. Well, obviously much prettier than that, but that's the general idea. So these two magnets are repelling each other. Now you might say, what about the lines inside? Well, hopefully you would have said that. Well, they're covered up by the colors here, but actually the lines go all the way through. They make complete loops. Here's a picture of two magnets with their opposite poles next to each other. And you're going to ask, where are the complete loops here? Here I have leaving the North Pole, goes into the South Pole here. It's going to go through the South Pole, and let me pick up the pen again, then comes around like this and re-enters the South Pole and starts again. You have a complete loop. It just doesn't go from the north to the south and then stops. It has to go through the other magnet, come all the way around, and come out. Again, complete loops, and these two magnets attract each other, just like a plus and a minus charge would do. The Earth's magnetic field is very similar to that of a bar magnet, just a lot bigger. View the inside of the Earth here as a bar magnet, and we're going to put the south end up here and the north end up down here. Why? Isn't this the North Pole? Well, it is the North Geographic Pole, but let's look at which way the magnetic field lines are going. They're entering at the top, so that means that's the South Pole. That's the South Magnetic Pole. Because if we put a little piece of metal here, or even a little bar magnet, we said that a North Pole of a magnet will line up with the field lines. So we'll have a north pole there and a south there. But it's being attracted to this pole, so that must mean this is a south pole, just like we said. So that's kind of cool, that the north geographic pole is really the south magnetic pole, and vice versa, the south geographic pole is really the north magnetic pole. What's the origin of this strong magnetic field? Well, it's caused by the circulation of molten iron alloys in the Earth's outer core. We'll talk more about that later. Another little thing here is the magnetic poles are not exactly in the same spot as the geographic pole where the Earth rotates on its axis. It's a little bit off. It's not in the same place. The magnetic field extends from the core of the Earth to the outer limits of the atmosphere, a place called the magnetosphere. This picture over here, here's the sun, here's the Earth, and obviously that's not drawn to scale. The Earth isn't that close. It shows the interaction of the solar wind. This red stuff is the solar wind, and that's comprised of electrons, protons, alpha particles, heavy ions, atomic nuclei, all kinds of stuff that comes out of the fusion reactions within the sun. And the Earth's magnetosphere is this blue thing. The magnetosphere protects life on Earth because without it, all of this ionizing radiation would hit the surface of the Earth, and that would cause great harm, if not basically just wipe out life as we know it. Many of the particles in the solar wind are prevented from entering the Earth's atmosphere by the magnetosphere, and we'll talk later about how moving charges can have a force exerted on them by a magnetic field. That's coming up. So you can kind of see the shielding effect here. The solar wind's not getting through. However, some particles do get through, but what they will do is follow these magnetic field lines down to the north. That would be, let's say, the South Pole, the South Geographic Pole. This would go to the North Geographic Pole where Santa Claus is, because that's where the magnetic field is the strongest. That's where the lines are closer to each other, and it's a much stronger magnetic field. As these particles go through the atmosphere, they'll collide with the oxygen and nitrogen atoms in the atmosphere. They'll excite those atoms, they'll give them a lot of energy. Those atoms will then give the energy back when they go back to their rest state, and that energy will be given off in the form of light. The kinetic energy of all these particles, that energy transforms into light energy, and that's what gives us the aurora borealis and the aurora australis. These are also called the northern lights, and there are many great pictures of them on the web if you'd like to look at them. But this is one I found that actually shows what it looks like in space. Here's the North Pole, right? You've got the Arctic and you've got I think that's Greenland. Looks like it should be. Here's Norway, etc. You can see the circle it makes around the magnetic South Pole or the geographic North Pole. These lights are beautiful. You can see them in the higher latitudes. Sometimes they dip down to the northern United States, but if you're up in Alaska or Canada, you can see them. And this is a direct result of the magnetosphere protecting us from the sun's solar wind. The symbol for the magnetic field is B. And notice it's written in bold here, because another way to write the magnetic field is with the vector sign. Because the field is a vector, it has magnitude and direction. The unit of the magnetic field is the Tesla, capital T, where 1 Tesla equals 1 Newton over amp meter. Because the Tesla is such a large magnitude, another unit is frequently used called the Gauss. 1 Gauss is 10 to the minus 4th Tesla. Get a little perspective around this. The magnetic field of the Earth at its surface is 0.5 times 10 to the minus 4 Tesla, or 0.5 Gauss, which was probably one of the reasons they did this. So you don't have to write all these exponents here to talk about the magnetic field at the surface of the Earth. The units were named after Carl Friedrich Gauss, who lived basically 1800s and was a brilliant mathematician and physicist, and we'll hear more about Gauss in the APC physics course, and the Nikola Tesla, who was a brilliant inventor. He was an American immigrant, he was an engineer, he was a physicist, and he and Thomas Edison had quite a few battles about AC versus DC current. Tesla won. We use AC current in this country.